Welcome to Calculus. Today we will investigate finding absolute extrema of functions on a closed interval. We'll take a look at one example. Our first example here is a quadratic function f of x equals x squared minus 8x plus 17. And we're considering this function over the closed interval from x equals 2 to x equals 6. Our goal is to find all the points of absolute minima and maxima on the given interval. And then we want to graph the function with a table of coordinate points. So as we approach this question, we really need to think about the mathematical justification that would say that there should be actually an absolute minimum and an absolute maximum on this graph. And that justification is the extreme value theorem. So we should say what that is before we begin, because it will guide our progress here. So here's the extreme value theorem. And what this theorem states, make sure I spell it correct, extreme value theorem, is that if I have a continuous function over a closed interval, so if f is a continuous function, and we'll call this closed interval generally from a to b, is a continuous function on a closed interval from a to b, then what we can claim is that the function has both an absolute maximum and an absolute minimum within that interval. Then f of x has both an absolute maximum and an absolute minimum. And that is the justification behind this task. So definitely a quadratic function is going to be continuous. In fact, its whole domain from negative infinity to positive infinity is continuous. So if I'm taking a slice of that from 2 to 6, definitely it's eligible to be considered for this extreme value theorem. Now, what we'd like to do is, first of all, find whether this function has some kind of maximum or minimum that's just inherent to the function itself. And then we're also going to look at the endpoints at x equals 2 and x equals 6. So my first step when I'm approaching this type of question is I want to find a place on the function where the slope of the tangent line is going to be equal to 0. So if I've got a perfectly horizontal line like that, it's going to be at a point where the function has either a maximum or a minimum value. And the way that we find that tangent line with a 0 slope is by taking the derivative of the function and setting it equal to 0. So that's what I want to do first. I want to find, I'll call this f prime at c equals 0. And I'm really specifically looking for what is that c value. So let's start off, we'll take the derivative of this function f of x. So the derivative here is going to be 2x minus 8. And in order to find where that x value is, where the tangent line is perfectly flat horizontal, I'm going to set it equal to 0. And I want to solve that equation. So it's easy to do. It's just a very straightforward two-step linear equation. I'll add 8 to both sides. And that gives me 2x equals 8. And then to finalize, I would divide by 2. And that gives me the x value of 4. Now, as I look, that's definitely within my closed interval from 2 to 6. So I'm going to go ahead and calculate the y value just by plugging that 4 back into the function. So once I find this, I want to locate the exact coordinate. So I'm going to take this and calculate f at 4. So that's going to be 4 squared. Again, this is the original function, minus 8 times 4 plus 17. So that we just need to calculate out. So that's going to be equivalent to 16 minus 32 plus 17. And then if I add 16 and 17 together, that's going to give me 33. 33 minus 32 is going to be 1. So I've got a maximum or a minimum here at the point 4, comma 1. So I'm going to box that because that's really something that I'm going to need as I'm locating the max or the min, and I'll go ahead and graph it. My feeling is that that is a minimum since this is a quadratic with a positive leading coefficient. It's likely to open up. We'll see if that actually shows to be true. So then I want to think about then if that's the inherent extreme point, what about the endpoint? So we're really considering this function on a closed interval specifically from 2 to 6. So my second step is I want to identify the coordinates of the endpoints. And the way that I do that is I'm going to pick up the extreme values on the interval, so 2 and 6, and I want to plug those in just like we did with the 4 here to the original function and calculate the y values. So again, I'm going to pull the function. The first one I want to calculate is f at 2. That's the left-hand extreme value. So that's going to be 2 squared minus 8 times 2 plus 17. So again, I've got that substituted in. I would just want to evaluate now. 2 squared is 4 minus 8 times 2 is 16. That's negative 12 plus 17 is going to be positive 5. So I've also got this point 2 comma 5. And I can go ahead and plot that here. So 2, 5. And then let's calculate also f at 6. So just like we did with the other two substitutions here, we'll plug in 6 for x. So 6 squared minus 8 times 6 plus 17. So that's going to be 36 minus 48 plus 17. So if we add up 36 and 17, that's going to be 53, and then 53 minus 48 is again 5. So it turns out that these endpoints at 2 and at 6 are at the same y value. Both of those are at the y value of 5. So I'll go ahead and plot that other one, and then from the graph we can decide what our extreme values are and whether they're extreme minima or maxima. So this is definitely a quadratic, and I can get these values for 3 and 5 just by following the quadratic pattern. Those should be one above the vertex. And that'll allow me to graph this function on the closed interval. So there I've got my quadratic. And that really allows me to see visually what sort of extreme each of these points is. So we'll start with the one that we found at first by finding the slope of the 0. And that's right here at the vertex of this parabola. And that is clearly an absolute minimum. So I'm going to go ahead and label that as, we'll label its coordinate. So we found it by taking the derivative, setting it equal to 0, and then plugging that x value into the original function. So that is an absolute minimum. And then we can also identify both of these upper points, the one at 2 comma 5 and the one over here at 6 comma 5. Since those are identical y values, we would identify both as absolute maxima. And that completes this task. We've found all of these critical points on the closed interval 2, 6 for this function. We've graphed it, and then we use the graph to confirm and identify whether or not these points were absolute maxima or absolute minima. And it supports, as just an example, the extreme value theorem. Thanks for joining for this investigation of finding absolute extremes of functions on a closed interval. See you soon.